Okay, last example for tonight, and this one is on shifting the location of the initial conditions. Okay, so suppose we had this equation, y double prime plus 3y prime minus 4y equals 6e to the 2t minus 3. Well, automatically, if we have to do the Laplace transform of that, that's going to be way less pleasant than it would be if it was just e to the 2t. But here's what comes to the rescue. Here's the initial conditions. Y at 3/2 is 4, and y prime at 3/2 is 5. Well, those initial conditions are problematic because the equation we want to plug this into, remember, is that y is equal to s plus a times the quantity y naught plus y prime naught plus r, the Laplace transform of little r. And then that whole thing is divided by s squared plus sa plus b. We can't plug in these two initial conditions if they're not at 0, and these are not at 0. So let's go through the process of making them at 0 before we plug them in here. And we do that with a little transformation. I want to replace t by tilde t plus 3/2. And when I make that replacement, notice tilde t is t minus 3/2. So if my initial condition is 3/2 and I subtract 3/2 from it, that'll move it to 0. So now tilde t's initial condition is at 0. So I can rewrite both of these. Now it's y naught equals 4 and y prime naught equals 5. The problem is now I have to use this tilde t in the new function y and the new function r. So I have to rewrite this differential equation. Fortunately, it doesn't mess with the constants. It is going to change the nature of that function, and it just changes all these into a new y. So this is going to be y tilde double prime plus 3y tilde prime minus 4y tilde is equal to, and I'll go ahead and make that transformation. It's going to be 6 once I plug in that the new t is basically the old t minus 3/2, so it'll be tilde t is equal to t minus 3/2. If I subtract 3/2 from that, or excuse me, add 3/2 because it's tilde t plus 3/2, 2 times 3/2 is positive 3 minus 3, it's going to make it e to the 2 t tilde. And so now it doesn't look as bad because they kind of built in the fact that this one had to be transformed into that exponent, so it actually moved it back to a nicer location. Okay, well, now we're ready to solve this differential equation by using the Laplace method. The first thing I want to do is write my function for r. Remember, r tilde is going to be the Laplace transform of little r tilde, and that's little r tilde. And if I look on the table, the Laplace transform of e to the 2t is just 1 over s minus 2, so this is 6 over s minus 2. So that's the Laplace transform of the answer. Well, now I want to write that function. It's really y tilde because everything's transformed, so it's s plus a times y naught tilde plus y prime tilde plus r tilde, and that's all over s squared plus as plus b. Well, we can fill all this in now. So the numerator s plus a, it's going to be s plus 3 times y naught, which is 4, plus y prime naught, which is 5, plus the new r tilde, which is 6 over s minus 2, and then the whole thing's over a denominator of s squared plus 3s minus 4. Okay, so this then becomes my y function. And this one turned out to be pretty unpleasant in terms of partial fractions. This guy does factor, so it produces 2 terms, this one and this one. This one has all 3 factors in its denominator. This one only has 2. I worked it all out separately. The purpose for this example isn't to get caught up in partial fraction decomposition, but nonetheless, I worked it out separately. And this one just works out to be pretty easy. It's 3 over s minus 1 plus 1 over s minus 2. And these are both exponential functions. So when I write my y tilde, it's going to be equal to, the first one is 3 e to the x, or e to the t. And the second one is just e to the 2t. Well, of course, this is for y tilde, and now I want to transform it back. So these are t tildes, and of course I want to transform it back. If I solve for t tilde, it's t minus 3/2. So that goes in each one of these. So basically, if I want y, then y is equal to y tilde with t minus 3/2 substituted into it. So this will give me y of t, and that's going to be 3e to the t minus 3/2 plus e to the 2 t minus 3/2. And that's it. That's the solution to this original differential equation at the point 3/2. After we did the transformation and substituted it and solved, we undid the transformation, so we basically moved it back to its old location. This allows you to use the Laplace method for any initial condition, no matter where it is. It is helpful if they're both at the same location, because we wouldn't want to do different transformations for the derivative than we do for the original function. So it is key that these both be at the same position if they're not at 0. Okay.